Good morning.
Good morning, sir.
Good morning, sir.
Uh, all of you are getting my screen.
Yes, sir.
Yes, sir.
Okay, so um, today we will start our discussion with the testing methods, right? That are used for the sequential logic design test, right? So in yesterday's lecture, what we have covered, that path sensitizing part, right? Then I discussed about the random test. That means that may be a combination of that two things. That means the cat model and uh, path sensitization. You can go for anyone. So now that means we have covered the testing methods for the combinational logic. Okay, again, I will summarize. What are the testing methods available for the combinational logic? First one is a stack model, right? Or fault model test. That is one and the same thing. Then second one is a path sensitizing. That is the second method. Third method is a random test. That means you have to use a combination of that both, right? Or you can use any one of that. So that is depending upon your application. So that is about the random test uh, method. Okay, so yesterday we have covered the combinational circuit testing methods. So now today we will start our discussion with the testing methods available for the sequential logic circuits, right? Testing methods available for the sequential logic circuit testing. Now, I told you there are major three techniques or methods that are available for the sequential logic circuit testing. Which are those? First one is the scan part testing, right? Second one, built-in self-test. In again that built-in self-test, there are some methods such as LFSR, that means linear feedback shift register is there. Then signature analysis is there. Then built-in logic block observer, that is again one of the sub techniques in that built-in self-test. So these are the sub methods in that built-in self-test. And the third one is boundary scan or JTAG uh, testing, right? Boundary scan or JTAG testing. So these are the three, what we can say, the major techniques that are available for the sequential logic circuit testing. Okay. Now we will discuss the first method, that is scan part testing. Now, uh, what do you mean by this scan part testing? And actually, now you can understand. Now you consider any chip or any what we can say digital ASIC, that is application specific integrated circuit. What do you think? It is just a combinational circuit, or it is just a sequential logic circuit, or it is a mixture of both sequential and combinational logic circuit? What do you think? So these are the normally mixture, or we can say combination of combinational as well as sequential logic designs, right? So you cannot have only just a what we can say just a combinational logic design or sequential. No, you can go for what we can say either a combinational, sequential, or in that particular what we can say platform, one part will have just a combinational logic design, another part will have a sequential logic design, right? So that particular ASIC is mostly a combination of both, and that's why we have to go for the different testing methods available for the combinational logic design as well as sequential logic design, right? So nowadays you are all of you are aware of, there are digital ASICs are available in the market, right? Each and every electronic device nowadays that has some ASICs, right? That is application specific integrated circuit, means that meant for the that particular application only. For example, a very what we can say a common and your day to day life example, your Android phone mobile chip, that is a best example of ASIC. तुमच्या फोन मधली जी मेजर जो तुमचा चिप असते, राईट, दॅट इज द बेस्ट एक्झाम्पल ऑफ ASIC. का? दॅट इज द ऍप्लिकेशन स्पेसिफिक. बरोबर आहे, मोबाईलची जी काही एक ठराविक ऍप्लिकेशन आहेत, राईट, टू रिसीव्ह द कॉल, टू जनरेट अ कॉल, राईट, or what we can say different applications, for example, you have a camera, you have a Google search, that means you have to again connect to the DHCP server and all that. That means what is it has some specific applications, right, to operate, to store, and to enable different apps on your Android phone, right? You have again main job is to again it is a specific Android OS based opera system, right? On your Android phone, if you want to what we can say debug or use Windows OS like a Nokia phone, right? You know already Nokia phone uses the Windows OS. So if you want the same OS in a Samsung mobile that is Android based, it will not work properly. Why? Because it is a ASIC that meant for to run only for the Android OS, not any other OS. Even if you want to debug that Apple OS, right? So even that will not work properly. Why? Because that particular chip is that ASIC is designed for the Android OS only. The vice versa is the case with the Nokia mobile. Nokia mobile is only designed so that it will work properly with that Windows OS. Clear? If you want to again debug the Android OS using the same hardware, it will not perform well because that ASIC is not meant for that, right? So that is what we can say nowadays. You are finding such a different ASICs in different electronic devices and circuits, right? That is application specific integrated circuit. And that a stable design of digital ASIC and systems are essential to obtain high reliability. Okay, means if you want that to be a very reliable, you have to test that ASIC. And nowadays it's a what you can say everywhere you find such a that application specific ASICs instead of a general purpose ICs and all that. No, you are if you design ASIC, it is always its performance will be always better. Why? Because it is meant for that particular application only, not a general purpose application. And then that's why we have to go for a different automatic and advanced testing methods, such as JTAG is available, then scan part testing is available, then built-in self-test is available. So these are the kind of automatic testing methods that can test that entire ASIC or entire chip, right? And that's why that are very much useful. Okay. And in addition to that, again, there are some prominent testing methods are available that I mentioned you. That is linear feedback shift resistor is there, built-in self-test is there, built-in logic block observer is there, right? Then JTAG, most what we can say most prominently used testing methods in case of ASICs, FPGA, CPLD, that is JTAG, right? Even your Android, Arduino chips have some Arduino chips has that facility of having JTAG port, right? Now, what is your job? Just connect that JTAG cable to your PC and to that ASIC, and you can simply check that IC. Your job is over. You need not require any external testing circuitry and external hardware, right? So that is the advantage of having that JTAG interface. So the what we can say the testing is very easy with that JTAG interface, right? And Nowadays, many actually boards provides that JTAG port with JTAG cable. So that is all about the testing. So now we will discuss about this scan part testing method and what is it actually. This actually scan part testing that involves a specialized flip-flop, right? Or sometimes it can be a specialized latch that allows data to become scanned in for a control and to be out for observation, right? That means that D flip-flops you are able to see. So these are the normally specialized flip-flops that are used in this scan part testing. And what is role of that flip-flop? That allows data to be scanned, right? That allows data to be scanned and it is to be produced for observation, right? And it can be activated in scan mode for test purpose, right? So this data in and out, right? In for the control, that it is scanned in for the control and out for the observation, right? And what is purpose of using this? To test the circuit, to test that particular combinational circuit, or you can connect their sequential circuit also, no problem, right? So this what is what we can say major feature of this scan part testing is this scan part testing improves the observability as well as controllability by enabling all storage nodes to be controlled observed via a serial scan path. That means when you simply enable that serial scan part, that means the scan in pin, then it has a better observability and controllability that it provides, and the testing is very effective and very efficient. That so that particular combinational circuit is your DFT, actually designed under test, right? Or designed for testability, you can say it is DFT. That means which the particular IC, ASIC or chip that you want to test, that is nothing but the DFT, designed for testability. Now with this scan part method, the observability, that means what? With a minimum number of test sets, you can find, or you can what we can say, get the maximum out maximum test outputs. Minimum number of test vectors, you are able to get the maximum number of test outputs, right? म्हणजे तुम्हाला खूप कमी टेस्ट वेक्टर मध्ये जास्तीत जास्त तुम्हाला व्हॉट वी कॅन से, तुम्ही दॅट पार्ट ऑफ दॅट डीएफटी यू कॅन टेस्ट, बरोबर आहे? विथ मिनिमम नंबर ऑफ टेस्ट वेक्टर्स यू कॅन चेक द मॅक्सिमम व्हॉट वी कॅन से नंबर ऑफ टेस्ट आउटपुट्स. म्हणजे टेस्ट वेक्टर लिमिटेड आहेत. एक टेस्ट वेक्टर दिला की त्या टेस्ट वेक्टरनी बराचसा सर्किट किंवा बराचसा पार्ट त्या सर्किटचा टेस्ट होतो. सो दॅट द नंबर ऑफ टेस्ट वेक्टर्स यू विल रिक्वायर्ड इज व्हेरी लेस. ओके, नाउ we will discuss about the test principle of this scan part testing. Now what is the test principle? म्हणजे हे कसं कॅरी आउट करायचं स्कॅन पार्ट टेस्टिंग? Now the first step is enable scan mode and scan in control data. म्हणजे पहिली स्टेप काय? तो स्कॅन मोड इनेबल करायचा, राईट, आणि स्कॅन इन कंट्रोल डेटा त्याच्यातनं पास करायचा. हा स्कॅन इन आहे, this particular is nothing but scan in. So you have to enable म्हणजे काय? You have to make it logic 1, right? Enable करतो म्हणजे आपण काय करतो? We are simply activating that pin. Activating म्हणजे काय? We have to connect that to a logic 1. Okay, so first step is enable scan mode and scan in control data. This is the first step. Now next, disable scan mode and clock chip 1 cycle. Okay, स्कॅन मोड आणि स्कॅन कंट्रोल मोड इनेबल करा. म्हणजे काय? त्याच्यात जो काही तुम्ही स्कॅन सिरियल डेटा जो तुम्ही स्कॅन करायला पाठवणार आहात तो त्याच्यात पाठवायचा, ते इनेबल करायचं, बरोबर आहे? नेक्स्ट काय करायचं? यू हॅव टू डिसेबल दॅट स्कॅन मोड. आता स्कॅन मोड डिसेबल करायचा आणि यू हॅव टू अप्लाय द क्लॉक पल्स. हे जे इथं क्लॉक टर्मिनल दिसतंय तिथे तुम्हाला एक क्लॉक पल्स अप्लाय करायची आणि स्कॅन मोड त्यावेळी डिसेबल करायचा. And the third step, again enable the scan mode and scan out observing data. परत हा स्कॅन मोड जो आहे तो इनेबल करा आणि हा स्कॅन आउट जो आहे तो इनेबल करा अँड ऑब्झर्व द आउटपुट डेटा. सो these three steps you need to follow. कुठली अगेन I will repeat. First, enable scan mode and scan in control, right? हा स्कॅन मोड इनेबल करायचा, स्कॅन इन कंट्रोल इनेबल करायचा. नेक्स्ट, disable the scan mode and apply a 1 bit clock pulse. एक क्लॉक पल्स अप्लाय करायची. थर्ड स्टेप, enable scan mode. Again you have to enable scan mode and scan out observing data. This scan out you have to observe the data, right? So in this way you can go for this scan part testing, right? In this way you can go for this scan part testing. Now how to generate the test vectors for this, right? So for this scan part testing you have ATPG, that means automatic test pattern generation. You have this ATPG program that will generate a random test vectors automatically. म्हणजे तुम्हाला इथे आपण पहिल्या मेथड्स मध्ये काय करायचो, बरोबर आहे, मॅन्युअल टेस्ट वेक्टर द्यायचो, बरोबर आहे. आपण जे स्टॅकॅट मॉडेल होतो तिथे आपल्याला मॅन्युअल टेस्ट वेक्टर द्यावे लागायचे. आता या केसमध्ये काय, if you are using that ATPG, that means automatic test pattern generation, then your job is over, right? It will automatically generate the test patterns randomly and it will apply to that circuit. It will apply to that circuit, right? And how actually it works? See, when you are enabling this scan mode, बरोबर आहे, हा स्कॅन मोड तुम्ही इनेबल करता म्हणजे तुम्ही काय करता, हे मक्स इनेबल करताय. कारण हे स्कॅन मोड कशाला कनेक्ट आहे बघा, टू द सिलेक्ट पिन ऑफ मक्स. म्हणजे तुम्ही हे मक्स सिलेक्ट केले, बरोबर आहे. आणि हा स्कॅन इन मोड पण तुम्ही इनेबल केला. मीन्स व्हॉट, यू हॅव ऍक्च्युअली इनेबल्ड दॅट मक्स. दॅट मीन्स नाउ मक्स विल पास इट्स आउटपुट इनपुट टू द डी फ्लिप फ्लॉप. आणि आता मक्सचं इनपुट कुठे आहे, फ्रॉम दिस कॉम्बिनेशनल लॉजिक सर्किट त्या मक्सला इनपुट आहे. दिस इज द फर्स्ट स्टेप. व्हॉट विल हॅपन इन नेक्स्ट स्टेप, आता नेक्स्ट स्टेप मध्ये आता हा स्कॅन मोड तुम्ही डिसेबल करणार आहात, राईट. दिस स्कॅन मोड इज डिसेबल. नाउ दिस मक्स आर डिसेबल्ड. आता ते मक्स आउटपुट पास करणार नाहीये. आता काय करणार आहे, तुम्ही क्लॉक अप्लाय करणार आहात. क्लॉक अप्लाय म्हणजे काय, व्हॉट एव्हर द इनपुट ऍट दिस डी फ्लिप फ्लॉप इट विल पास टू द आउटपुट साइड, राईट, as well as it has connected to this mux, right? It has connected to this mux input also. It has connected to this mux input also, right? Now again third step काय आहे, परत हा स्कॅन मोड इनेबल करायचा. म्हणजे हा मक्स इनेबल होणार आणि यू हॅव नाउ यू कॅन, आता ऑलरेडी तुम्ही हा डेटा डी फ्लिप फ्लॉप मध्ये पास केलेला आहे. सो यू कॅन एबल टू ऑब्झर्व दिस डेटा ऍट दिस स्कॅन आउट पिन. You can observe this data at the scan out pin, right? So this is how you can go for this testing of this combinational logic unit, or you can say DFT, that is designed for testability. Design for testability म्हणजे काय, जे तुम्हाला टेस्ट करायचं आहे, जे डिझाइन, जे ASIC, जो IC, जे बोर्ड तुम्हाला टेस्ट करायचं आहे, that is nothing but that design for testability. In this way the scan part testing will work. Okay, now we will discuss the advantages of this scan part testing. Now what are the advantages? The first advantage is test vectors can be generated by ATPG program, that means automatic test pattern generation. हा सगळ्यात मोठा ऍडव्हान्टेज आहे की टेस्ट पॅटर्न जे आहे ते ऑटोमॅटिकली जनरेट होतात, बरोबर आहे. तुम्हाला मॅन्युअली जनरेट करायची गरज नाही. दिस इज द फर्स्ट ऍडव्हान्टेज. What is the next advantage? Observability, controllability programs do not have to be considered during the design phase. बरोबर आहे. म्हणजे ऑब्झर्वेबिलिटी आणि कंट्रोलॅबिलिटी हे प्रॉब्लेम जे आहेत यू नीड नॉट टू कन्सिडर ड्युरिंग द डिझाइन फेज. ओके, बिकॉज इट्स when you have to what we can say use this scan part testing, it will also check the observability and controllability of that design. So in design phase you have to least bother about that particular steps of the design. Okay, now the third one is a testers do not need to have a complex test vector generation capability for all pins of the chip, right? Means as it is that testing vectors are generated automatically. As a tester, you did not have to generate that complex test vector, right? That means you can have a simple, what we can say, that if you happen to use this scan part testing, you need not have to go for any complex test pattern generation. No, because it is already the care is taken by that ATPG, automatic test pattern generation circuit, that will generate the automatic test vectors and it will apply to the circuit, and you can simply go for the scanning of that circuit by using that three steps: enable scan mode, then enable scanning data, then disable scan mode, enable clock pin, then again enable scan mode and observe the scan out, right? तुमचा एवढाच जॉब आहे फक्त ते इनेबल डिसेबल करणे, क्लॉक देणे आणि डेटा ऑब्झर्व करणे, बरोबर आहे. टेस्ट वेक्टर जनरेशन विल बी टेकन केअर बाय ATPG program, that is automatic test pattern generation. Clear? So these are the what we can say advantages of this scan path. Now what are the disadvantages of this scan path? So hardware overhead, because you can able to see for the DFT you have to design this D flip flop, then mux and all that connections and everything, right? So means hardware overhead on the circuit will get improved or increased, बरोबर आहे. एक्सटर्नल ॲडिशनल मल्टिप्लेक्सर, डी फ्लिप फ्लॉप किंवा लॅचेस यूज करणार असाल तर लॅचेस, हे सगळं ॲडिशनल हार्डवेअर तुम्हाला लागणार, त्याशिवाय तुम्ही हे करू शकत नाही. सो दॅट दिस इज द डिसएडव्हान्टेज. अँड व्हॉट इज द नेक्स्ट डिसएडव्हान्टेज? स्पीड डिग्रेडिंग, बरोबर आहे. हे सगळं करताना स्पीड सुद्धा कमी होतोय. का? कारण तुम्हाला प्रत्येक ते एकदा इनेबल करायचं, मग स्कॅनिंग डेटा द्यायचा, परत ते डिसेबल करायचं, मग क्लॉक द्यायची, परत स्कॅन इनेबल करायचा आणि डेटा ऑब्झर्व करायचा. सो इट फॉर एव्हरी स्टेप यू हॅव टू फॉलो दिस 3 स्टेप ऑपरेशन. सो द स्पीड किंवा टाइम रिक्वायर्ड टू टेस्ट दॅट डिझाईन फॉर टेस्टॅबिलिटी इज व्हेरी लार्ज. टाइम जास्त आहे म्हणजेच काय, स्पीड कमी आहे, बरोबर आहे. वेळ जास्त लागतोय म्हणजेच काय, तर त्याचा टेस्टिंग स्पीड हा कमी आहे. सो स्पीड डिग्रेडेशन, दिस इज द second disadvantage of this scan part testing. Okay, now this is about the scan part testing. So what I have explained you, the same thing it is explained there. Okay, so this is about the scan part testing. This is the example of the scan part testing, how actually that what we can say DFT will look like. So this is the circuit, right, that is designed for testability, and this is your scan part testing unit. So you can simply you have to follow this 3 steps: enable scan mode, then give scanning data, okay, then disable scan mode, give the clock pin, again enable scan mode and observe the scan out. So these are the 3 steps you need to follow. समजले का?
Yes, sir.
Okay. Now next type, or you can say next method of this sequential logic testing is nothing but built-in self-test. Okay, built-in self-test. Now we will discuss about this built-in self-test method. Now what is actually this built-in self-test method? Right, now all of you know, as the complexity of this individual VLSI circuit, right, nowadays getting what we can say the complexity increases day by day of the VLSI circuits, because we are going towards the nanotechnology, we are going towards the ASIC and all that things. So obviously the complexity of the circuits are going to obviously increase, and obviously the test generation and application becomes expensive. If you are increasing the complexity, so obviously to test that circuit, so complexity of the testing is also increases automatically, because anyway if you are no matter how complex is your circuit, anyway before what we can say actually deploying to the market, you have to test that circuit, बरोबर आहे. Circuit you have designed, okay, that is okay, but before deploying to the market, anyway, anyhow, you have to test that. Without testing, you cannot deploy to the market. बरोबर आहे. म्हणजे कॉम्प्लेक्सिटी सर्किटची वाढली आहे. ओके, यू हॅव अचीव्ड दॅट कॉम्प्लेक्सिटी लेवल, यू हॅव डिझाईन दॅट सर्किट, गुड थिंग. पण ते कॉम्प्लेक्स सर्किट चेक करायला पण टेस्टिंगची कॉम्प्लेक्सिटी पण वाढली आहे. कारण विदाउट टेस्टिंग तुम्ही ते मार्केटमध्ये लॉन्च करू शकत नाही. बरोबर आहे का रे? कारण ते बरोबर चालतंय का नाही चालतंय, त्याचं फंक्शनिंग बरोबर होतंय का नाही, त्या आसिकचं किंवा त्या आयसीचं किंवा त्या टार्गेट बोर्डचं जे काय तुम्ही डिझाईन केलंय त्याचं ते चेक करणं तुम्हाला भाग आहे. विदाउट चेक केल्याशिवाय हाऊ यू कॅन सेल इट टू द कस्टमर? नो. सो एनिवे, though the complexity of VLSI circuits are increasing, the testing complexity is also increasing. And obviously, if the testing complexity increases, so again some additional hardware or some additional software for the testing are also increasing. That means cost is also going to increase. So that is the what we can say total cycle of this. Okay, now this uh, very difficult problem associated with this high speed at which many VLSI systems are designed to operate, right? So at high speed means what? Nowadays many VLSI chips or ASICs are operating on a clock of say megahertz or even kilohertz frequency, right? Means at each clock pulse, right? The internal operation will occur. At each clock pulse, some what we can say data in or data out will take place, and that clock pulse is of frequency in kilohertz or megahertz. That means the speed of that particular chip is tremendously high. And to check such a high speed circuitry, you must have such a robust and what we can say effective testing method with you, right? एकतर कॉम्प्लेक्सिटी वाढलेली आहे, त्या कॉम्प्लेक्सिटी बरोबर काय स्पीड पण वाढलेला आहे. ऑपरेटिंग स्पीड ऑफ द सर्किट इज ऑल्सो इन्क्रीज, राईट? सो टू टेस्ट such a complex and high speed circuit, you must have such a robust and effective testing methods with you. ते सर्किट जसे हाय स्पीड आणि कॉम्प्लेक्स सर्किट चेक करायला तुमच्याकडे त्याच्या टेस्टिंग मेथड्स पण अवेलेबल असल्या पाहिजेत. बरोबर आहे? अँड दॅट्स वाय the what we can say the developers have launched this built-in self-test method, right? This built-in self-test method means what? Built-in self-test, as the name indicates, the circuit with self-testable facility. म्हणजे ते सर्किट स्वतःला चेक करणार. आलंय लक्षात? ते सर्किट स्वतःची फंक्शनॅलिटी चेक करणार. दॅट इज built-in self-test. So this figure you can able to see, this is the typical block diagram of this built-in self-test. So at the start you have that test vector generator, you have CUT, that is circuit under test, or you can say design for test or design for testability, that is one and the same thing. And finally you have a test result compressor and signature. That means whatever the test results you are getting from that circuit, you have to compress that and it will generate a signature, and you have to analyze that signature. That signature is nothing but the fault detection. That signature is nothing but fault detection. From that signature pattern, you can easily able to identify which fault is there in circuit or it is flawless, right? From that signature analysis, you can decide whether there is a fault in the circuit or there is not. Okay. So this is the generalized block diagram of this built-in self-test. Now again in that built-in self-test, you have different methods. As I mentioned you have linear feedback shift method, then you have built-in logic block observer, right? Then you have signature analysis, right? So these are the three commonly used methods for this built-in self-test. Now we will discuss the first method, that is linear feedback shift resistor, right? LFSR. So this is the typical diagram of the LFSR. Now this LFSR model is that of finite state machine comprising storage elements and modulo 2 adder, that means your XOR gate connected in a feedback loop as indicated in figure. Okay, so this particular arrangement is what you can able to see the different storage elements of D flip-flops, then one modulo 2 adder, that means your XOR gate, and the output of last flip-flop is feedback to the XOR gate. That means it has one feedback loop as well as two modular to adder and different storing elements. That is the D flip flop, you can store data. So you can say D flip flop is nothing but your storing element, right, or memory. Then you have a modular to adder, right, and up with feedback loop. So this is the typical circuit for the linear feedback shift register. Now this technique can be applied in a number of ways. So you can apply this technique in number of ways. Now one thing I want to clear, why you are saying that it's a linear feedback shift register, right? So in digital systems, how you can verify the linearity property? Okay, in analog systems, you have different theorems. So for example, if you say that particular circuit follows the superposition theorem, you can say it's a linear circuit, right? Now, in case of the digital systems, how you can say whether that particular digital system is a linear or not? Can anyone? How you can identify the linearity of the digital circuit? So I will discuss linearity of this digital or you can say this linear feedback shift register is that if a modulo 2 adder of any input, if modulo 2 adder of any input, the output of that modulo 2 adder is belong to the set of that input, then you can say that circuit is linear. Means, for example, here you can take a modulo to adder, that means that XOR addition of any input provided by you, and if that output, that means whatever the output generated by that XOR gate, if that output is also valid input, then you can say that circuit or that particular system is linear. Okay, and you can see in this case, you take any modulo to adder, that means that XOR addition of any with a random input, and you can find whatever the output it will generate, that is also a valid input, then you can say it's a linear circuit. Okay, so this is about, and that's why we can see it as a linear feedback shift register. Okay, now you can apply this technique in number of ways, including random number generation. Then you can have the polynomial division for signature analysis. Then you can have n-bit counting, and this LFSR can either be a serial or parallel. Means you can take its output serially or you can take its output parallelly, depending upon your application. Now, the differences being the operating speed and the area of particular chip that is used for the parallel LFSR and serial LFSR. That means there is only a what we can say design difference between the parallel linear feedback shift register and serial linear feedback shift register. So you can take the output parallelly or you can take the output serially, depending upon your application. So this is about the linear feedback shift register. And again, I will repeat, for what purposes you can use this LFSR circuit. So you can use to generate a random number, then for polynomial division for that signature analysis, and for n-bit counting, right? So these are the different use of this linear feedback shift register. Okay. Now next point is this single input compressor circuit, and it is not there in your syllabus. This MIC is also not there in your syllabus. Okay. So this figure shows the combination of this MIC, SIC, and this pseudo random. It is not part of your syllabus. Yes. Now next point is built-in logic block observer. Okay. So this is there in your syllabus. Okay. Now this part we will discuss tomorrow. Today we will stop here. Okay. From tomorrow's lecture we will start our discussion with this built-in logic block observer. That is the next type of built-in self-test. Okay. Do you have any query? कुणाल काही शंका आहे का?
No, sir.
Okay, fine. Then we will stop here. We will continue in next lecture.